In this video, we're going to look at a comparison test for improper integrals. Assume that f of x and g of x are continuous functions with f of x larger or equal to g of x larger or equal to 0. That means they're both above the x-axis on the interval from a to infinity. If the integral from a to infinity f of x dx is convergent, that means the area under the function f of x is finite, then the integral from a to infinity g of x dx is also convergent. Why is that? Well, we know that the integral from a to infinity g of x dx is less than the integral from less or equal to integral from a to infinity f of x dx. That's because the area under g of x is less than the area under f of x because f of x is above g of x. Alternatively, let's look at another case. If the integral from a to infinity g of x dx diverges, that means the area is infinity, then the integral from a to infinity f of x dx also diverges. So the improper integral from a to infinity f of x dx also diverges. And the reason is because the area under f of x is larger or equal to the area under g of x. And if the integral from a to infinity g of x dx diverges, then certainly the integral from a to infinity f of x dx must also diverge. We can see this from a diagram. If the integral under g of x is infinity, if the area is infinite, then the area under f of x must also be infinite because f of x is larger than g of x. Alright, when applying a comparison test for improper integrals, the goal is to prove that the integral a to infinity of g of x dx is less than a convergent integral. That's the only scenario when you can make actually a conclusion. Convergent integral. Let me put that in. So that we can conclude that the integral a to infinity g of x dx converges. Otherwise, if we prove that the integral from a to infinity g of x dx is less than or equal to a divergent integral, no conclusion can be made. Because when an integral is less than infinity, we can't say anything about its value. So we can't make any conclusion in this scenario. So key concept. When you do a comparison, make the integral either less than a convergent integral, or, as we'll see in the following page, make it larger than a divergent integral. So alternatively, if you're trying to prove that the integral a to infinity f of x dx diverges, then the goal is to prove that the integral from a to infinity f of x dx, the improper integral from a to infinity f of x dx, is larger or equal to a divergent integral. Divergent integral. Otherwise, if the integral from a to infinity f of x dx is larger or equal to a convergent integral, no conclusion can be made. Another key concept is when you're applying comparison theorem, make sure to compare integral f of x dx to a simpler integral whose convergence or divergence can be easily determined by just simple integration. Alright, let's look at an actual example. So here we have integral from 0 to infinity e to the minus x squared dx, and our goal is to prove that this improper integral converges. It is impossible to integrate f of x equals e to the minus x squared. There is no antiderivative, and we can't express the antiderivative of this function in terms of elementary functions. So we're going to split up this integral into the sum of two separate integrals. Integral from 0 to infinity e to the minus x squared dx is equal to integral from 0 to 1 e to the minus x squared dx plus integral from 1 to infinity e to the minus x squared dx. Let's consider the first integral. The first integral from 0 to 1 e to the minus x squared dx, we can see that the integrand e to the minus x squared is a continuous function on a closed interval 0 to 1. That means a definite integral from 0 to 1 e to the minus x squared dx converges. It has finite value. Let's actually make a drawing of that. So here's the function, e to the minus x squared. It comes down like this. Let's label this as y, and this is x, this is 0. This is the function, y equals e to the minus x squared. And from 0 to 1, you can see that the e to the minus x squared is a continuous function. For this reason, the area under the curve must be finite. That means the definite integral converges. So it remains to prove that the second integral converges. We have to show that. All right, so let's do that. We have integral from 0 to infinity. E to the minus x squared dx is equal to integral from 0 to 1, e to the minus x squared dx plus integral from 1 to infinity, e to the minus x squared dx. And in the last page, we showed that the first integral, this definite integral, converges. And our goal now is to prove that the second integral converges. Now, we know that x is larger or equal to 1. So let's multiply both sides by x. We get x squared larger or equal to x. Now multiply both sides by negative 1. So we get minus x squared is less than or equal to minus x. Now let's exponentiate both sides. We get e to the minus x squared is less than or equal to e to the minus x. So you can see how we're building up the comparison. So now we can say, we can basically, since we know that e to the minus x squared is less than or equal to e to the minus x, when x is larger or equal to 1, we can just integrate both sides from 1 to infinity, e to the minus x squared dx. And this has to be less than or equal to integral from 1 to infinity, e to the minus x dx. Let's integrate this. So we have integral from 1 to infinity. This is an improper integral, e to the minus x dx. Let's write it in proper notation, improper integral notation. Limit t goes to infinity. Integral from 1 to t, e to the minus x dx. That's equal to limit t goes to infinity, e to the minus x, divide by negative 1. That's due to the substitution rule. We're letting u be equal to minus x. Then we make some room here. U equals minus x, and du equals minus dx. All right, so limit t goes to infinity minus e to the minus x, evaluate it from 1 to t. Apply the fundamental theorem of calculus. We get limit t goes to infinity minus e to the minus t minus minus e to the minus 1. So that's equal to limit t goes to infinity minus e to the minus t plus 1 over e, because minus minus makes plus. And if we take the limit as t goes to infinity of a negative exponential, that's going to go to 0. We get 0 plus 1 over e. So what we have shown is that the integral from 1 to infinity, e to the minus x squared dx, we did comparison theorem, we applied comparison theorem. This is less than or equal to integral from 1 to infinity, e to the minus x dx, which we proved is equal to 1 over e. That means this integral converges. And by comparison theorem, the integral from 1 to infinity, e to the minus x squared dx, split into the sum of two separate integrals. Integral from 0 to infinity, e to the minus x squared dx, is equal to integral from 0 to 1, e to the minus x squared dx, plus integral from 1 to infinity, e to the minus x squared dx. The first integral, we proved it converges. And the second integral, we applied comparison theorem, and this also converges. So we have a sum of two separate, we have a sum of two convergent integrals. So we have proven that the integral from 0 to infinity, e to the minus x squared dx, this part also converges because it's a sum of two separate, two convergent integrals. Let me put this in, conclude that integral from 0 to infinity, e to the minus x squared dx also converges. So let's look at a diagram. The key concept is that you can see how e to the minus x squared dips below e to the minus x when x is bigger than 1. So when we did our comparison theorem, we basically showed that the area under e to the minus x squared is less than the area under e to the minus x. And that's how we apply the comparison theorem, and we prove that the integral from 1 to infinity e to the minus x squared dx also converges. All right, thanks.